Oh, come on, everybody move together. No. So my name is Gary Strand. I'm a software engineer in CGD in the climate change research section, the climate change prediction group. Oh, excuse me, very long range numerical weather prediction group. My apologies. Climate is no longer an acceptable word, apparently. And I'm going to talk today about some recent experiences and future projects involving CESM and only CSM at this point that we've been doing for the last few years, and then what's coming up with this thing called CMIP 6. And unfortunately, I didn't tell Paul that I needed the lapel mic, so I have to stand here. So, like I said, I'm Gary. This is primarily what I do, data support for our group, our section, the project as a whole, the entire division, and then our thousands of users around the world. I work as an informal liaison. I'm actually not part of CESM itself. I help out a lot. Talking about how CSM does data, how CSM, what its data plans are, its data management plans are, to various groups around NCAR and UCAR, Department of Energy, which is the agency that funds me, and then other internal and external data focus groups. I've talked with NOAA and NASA and folks in the UK and Germany and Japan and China and stuff like that. I've been to a few international meetings. That's always interesting. There's a global organization for Earth System Science Portals. It's kind of this giant umbrella group that covers not just climate model data, but observed data, all kinds of data. And I've been to a few of those meetings. We talk a lot and realize what kind of problems we have that are similar across all the groups. We have a small little machine in our section that is called Silver, although it's being replaced, that we have about 260 terabytes of disk on. That's going to change to about 400 here in a couple months. We use that primarily as a permanent archive of the data that our scientists or our group scientists are interested in. The nice thing is it's never scrubbed unless I get irritated at somebody, and then I can just take their data off there if I feel like it. But that's, in some ways, it's much, much, much smaller than Glade, but we can have stuff stay there for years or decades, which has been the case. I supervise one person. Her name is Alana Stern down in Durango. She does all of our ESG publishing and does most of the data post-processing. I mint digital object identifiers for our data sets and other things like, for example, the current version of the newest version of the model, CSM2, now has a DOI. One of our big data projects has a DOI. Provide general computing support to anybody that asks me. I'm primarily a data wrangler, data manager, data scientist, and also a data archaeologist. I just had one of our atmospheric scientists ask if anybody had some late 90s era model data. I do, so I passed it on to him. And then, of course, I do some coding from time to time. So this is, I toss this in there because everybody seems to think this is funny. So there's supercomputer, machine that takes one problem and turns it into many, many more. And from a data-centric point of view, which is mine, I almost don't even care what the supercomputer is. My concern is, where does the data go? Who gets it? What format is it in? All this other stuff. How fast the model runs and all this other stuff. I really don't pay that much attention to it. What our allocations are, how much we've used, how much we have left. That isn't of terribly much interest to me. I just want to know, all these compute hours that generate tons and tons and tons of data, what happens to it after that? Somebody has to pay attention to it because that's the only way we know how the model is working.
Pay attention to that.
Pardon?
More people will need to pay attention.
Well, yeah. Yeah. So this was a paper that came out in 2011 in Science. So you can see here the volume of worldwide climate data is expanding rapidly. The ease of access and finding what's needed if you're not a climate scientist is daunting, and it still is to some extent. There is yet to be a Google for data. It's getting there, but at least projects like DSET here at NCAR have recognized this problem and making great advances in fixing this. And this paper, when it came out, I thought these numbers were a little high, I mean, here we are, what, a couple slots before 2020? And actually, it's not too far off. Our holdings here, well, I'll tell you how much we have. But if you collect all the climate model output from around the world, these numbers actually are pretty close. Now, whether or not that continues into the future, we'll see. But so this is where we're talking, you know, let's see, what's that, 300 petabytes in 10 years or so, 15 years? I don't know if I'll be around to have to mess with it. We'll see. So the question is, does CSM have big data? Yes, it does. On the left axis is the annual volume of data that we archive. This isn't just here at NCAR, but at all of our major computing sites. National Energy Research Supercomputing Center at NERSC out in California. Oak Ridge, we have data located there. The Argonne Center in Chicago, near Chicago, and also a little bit of data at NCSA in Illinois. So this is about what this is what we've been dumping out the last few years. You can see there's some drops and dips. That last point there is actually only through the end of the first quarter of 2017. So we're a quarter of the way through the year, and we've already archived roughly 1,500 terabytes. So that doesn't bode well for the rest of the year because that implies somewhere on the order of 6. And then here's our cumulative total. As of now, we're just under 12 petabytes of data across all of our computing centers. So these spikes here, this was CMIP 3 back in 2004, 2005. CMIP 5 starting in 2011. These community projects, which I'll talk a little bit more about later. But you were asking, Seth, you know, CMIP 5 the big thing? No, not anymore. And of course, we don't just hold it all, we send it out all over the planet. So here's what our CMIP 5 data distribution looks like. This is just through our portal here at NCAR. Much of this data has been replicated elsewhere on the planet and has been distributed via those means. I have no idea how much that is. So, but the interesting thing here is you can see it's kind of flattened out a little bit. CMIP 5 is now becoming somewhat dated. People have gotten what they want pretty much, and so the volume going out has kind of tailed off, it's flattened. But we have lots more data to send out to people. So in the last, well, so far we've distributed well over 2 petabytes of our data. And that's just through the ESG portal here. There are other sources. So I'll talk about some recent big data projects post CMIP 5. First one that we did was this thing called the Large Ensemble, which was a set of about 120 runs in total that started in late 2013, and occasionally a new run comes in. As you can see there, the grand total is about 300 terabytes of data, and it's all sitting on our HPSS here. And we took advantage of the compression ability of NetCDF4. Otherwise, this data volume would have been about 60%, or more than twice as large, actually, on the order of probably 800 to 900 terabytes. So that was a good thing. And then we also used the same techniques for this last Millennium Ensemble. A lot fewer simulations, but each one's extremely long, on the order of 1,200 years. So the total number of data, or total number of years simulated is more than double. Total volume, though, is about the same. Not near as much was saved from each run as was saved from this large ensemble run. So the way we did this with the large ensemble is, so we had a set-aside space on Glade, roughly 400 terabytes in size. And as the model was running along, I was following along and post-processing, archiving the post-process data and getting rid of the original model output. Except for a couple of the first couple of cases, we did not actually archive the original model output to HPSS. That was a decision that was made because actually most of the people that use our data are interested in what we call time series format. It's a single field across all times rather than all fields at a given time. I mean, if you're interested in looking at surface temperature, sea ice area, soil moisture, you don't care about all the other stuff that comes out of the model at the same time. You're interested in only that field, but you want to look at a temporal analysis over a long span of time. And that data is at least 80 to 90% of our downloads is people interested in that. So what we did was we took advantage of that knowledge, and the column on the left there is about how many terabytes per month we were dumping out from the model, and the red line on the right is the grand total. So we actually generated over 2 petabytes of data. But you wonder, there's our 400 terabyte quota, so we constantly had to follow along the model as quickly as possible, doing this post-processing and archiving and clearing off those files. I've never erased 100 terabytes of data at once. It's a little bit daunting, I can tell you. Is it RM? Oh, okay. It's a little bit scary. And the way we did this was we used the netcdf operators in serial mode, which is about all they can do actually. So here's different time slices of the model. You can think of these as months. There's all the fields in at each time. You transpose those, so you get all the times for field 1, all the times for field 2, and all the times for field 3. This is not terribly efficient, but that was the tool that we had available to us. So as part of that, we decided there's got to be a better way we can do this, plus with CMIP 6 on the horizon and the experience with CMIP 5. So CSM and the software engineering group started this workflow re-engineering project. This was about late 2015, I think, or maybe a little bit before that. So this is the way we used to do things. This was a little different than what we did on the large ensemble, but this is what we did for CMIP 3 and CMIP 5. Run the model, dump directly to HPSS. When a run is done, pull the data back, do the serial diagnostics, the serial time series generation, and then you do your analysis. This is what killed us with CMIP 5, because writing to HPSS and then pulling it back is extremely slow. And the main reason we had to do that, well, 2 main reasons. One, inertia, that's the way it's always been done. And secondly, we simply did not have enough disk space to store an entire model run at one time. That is no longer the case. Glade is now amply large enough to store many model runs. Not all the model runs, but lots of them. So this is what we did, not for the large ensemble, but for the later part of the LME. Run the model, archive it on, or just keep it on disk. Use this new tool called Pi Reshaper, which I'll talk about in a second, if you need to do diagnostics. And then it turns out we did always save to HPSS. That wasn't optional. But this saved us so much time and so much effort, and HPSS tapes. This worked wonderfully. I'll talk a little bit about how that works. So the nice thing is, depending on how many fields you have in your output, which can be anywhere from a small handful up to hundreds, you assign those to as many processors as you have space on the machine, and it processes them all simultaneously. So you get well, I'll show you here the timings. The speed up can be actually rather spectacular. And at the end, you get the exact same output as you did before. So here's some numbers from early testing of this tool. You can read the details. So the speed up is anywhere between a factor of 5 and 10, depending on exactly the configuration of the model and how much output there is. In the latter part of the last Millennium Ensemble project, I ported this code into the scripts that they had been using to do their post-processing, and particularly for the ocean data, which is extremely large. What took a week, they could do in a day. So that made everybody happy, because then you can do many post-processing jobs simultaneously and get it done a whole lot faster. Yes, Seth?
Can you suppose you've only got one variable that you're looking at? Can those high reshaper run parallel to each other?
What do you mean one variable it by default will pull out all the fields that are in the model output and generate a single file for each one.
Okay.
So it runs most efficiently that way.
Okay. But if you've only got one field in the first place,
There's no win to that, really.
okay.
It's moderately faster, but not hugely faster.
Okay. So it's really the separating out the field that's a lot faster.
Right. because it can be writing, as many fields as the number of processors you toss at it simultaneously.
Okay.
And it also works really well. The scaling kind of tails off a little bit if there's a lot of time samples. So if you have a really high time frequency output like subdaily, you don't get the 10x scaling. It's more like 6 or 5x. But that's still huge. So the first time we ever tried this out on a production scale was this project we did at NERSC starting in late 2015. It was a decadal prediction project. So we ran 620 simulations. Each one is only a little over 10 years long, 13 output streams each. So what ends up coming out is about 9,100 time slice files per simulation, or about 1.1 terabytes per simulation, a grand total of, you multiply 620 by 1.103, you get about 670 terabytes. We did it again the following year with a slightly reduced output set and some model configuration changes, used the same technique. So the grand total is a huge reduction in the number of files and about 25%. Actually, that 672 should be doubled, roughly. So we ended up with slightly less than half the original model output. And it worked great. And then, since that worked so well and the scientists were learning a bunch of stuff from this set of runs, as part of ASD, we decided to extend that ensemble. So we did the exact same model configuration, except this time, instead of doing 10 runs for each set, we did an additional 30. So the first set of runs was done on Edison. This one was done on Cheyenne. A grand total of 1,860 simulations, almost 11 million model output files, roughly 6.1 terabytes per set of 10. So that's roughly 1.13 petabytes of model output, grand total, which was roughly the same order of magnitude as CMIP5, the whole thing. The way we did this is, okay, so there's your model run, writes to disk, call PyReshaper, write back to disk. And the nice thing about this particular set of simulations, all this was controlled by Silk, which is this workflow manager that Sherry Michelson, Kevin Paul, and others in the ASAP group, well, it's not the ASAP group anymore, whatever they call themselves now, over in Sizzle, has played with and set up for us to work with. So basically you set up what they call a suite for each model run, and it takes care of all this. It does it all automatically. It triggers the right, when a model run is done, it fires off a PyReshaper script, and then it moves on to the next model run. So all this was pretty much done automatically. I didn't have to intervene and run my scripts separately as the model runs were being completed. Once the set of 10 is done, we write that to HPSS, and then eventually we'll be publishing these to the Earth System Grid portal here, and of course analysis is underway. This was a really good test bed for CMIP6, and I'll explain what we're planning on doing for CMIP6 here in just a minute. So this is what our original set was, about 1.13 petabytes. After doing the transposition, exploiting the compression, and H-tarring each set of 10 runs for each variable, we only ended up with about 170,000 files on the HPSS, not the mass store, about 410 terabytes. So we cut the volume down by 60%, and the number of files by whatever the math is, 95%. And we did this in 46 days. CMIP5 was like 3 years. We did this in 6 weeks. So that's what we can do now with these parallel tools and the Silk Workflow Manager, is we can expedite this at an incredible rate. One of the advantages we had is we had a 750 terabyte partition on Glade, so that we could do the model runs there. The peak that we hit on that was roughly 600 terabytes of space actually used before I was able to drain it all off. And this 46 days includes time when HPSS was down, Cheyenne was down. So our effective throughput per day was actually, well, more than 10 terabytes a day, probably closer to 15, which isn't bad. That's about as fast as you can go. That's about as fast as HPSS can write, given that it's a shared resource and there's only so many tape drives. So let's jump ahead a little bit to CMIP 6. So this is give you an idea of the kind of data volumes from the past 3 CMIPs. So CMIP 2 back in 2000, we donated about 2 gigs. As I recall, I sent them 4 CDs of data, and that was all. It took like an afternoon. It was very nice to be able to do that. The next one, CMIP 3, we generated roughly 50 terabytes of model output and submitted roughly 10. And the way that was done was PCMDI out there at Lawrence Livermore was the central collection point, and they would ship around these 1 terabyte external hard drives to all the modeling centers. We'd fill it up and then ship it back, and then they'd send us another one. That was not the most efficient way to do it. My understanding is one got stuck in Russian customs for like a month. And because of, this was shortly after the big DOE hacking attack, and I think that was in spring of 2003 or 2004, I can't remember which year it was. So, and PCMDI being part of DOE was very worried about, being exposed to various security threats. So this was their solution. At one time we tried to buy some more drives so we could, get them going through more quickly. And they said, nope, we can't do that. You'll have to use only the drives that we have. And I think they only ended up buying like 15 or 20 of them. So I got very used to sending these drives back and forth and back and forth and back and forth. And of course, the drives being at that time were not that reliable. So sometimes one would get about half full and then quit accepting writes. So I'd say, well, fine, we'll ship that one back. It was a many-month process. And then CMIP 5, starting in late 2011 through 2014, we ended up generating roughly 1.2 petabytes of model output, of which about 170, 180 terabytes is what we submitted. Now, this time was completely different. All this data is hosted here. It is not located at PCMDI. They may have a replica copy, but the core archive is here. And because of the difficulty with CMIP 3, the grand total for that, all the modeling centers, the grand total was about 35 terabytes. And at that time, you could actually, 35 terabyte disk system wasn't that amazingly huge, although by today's standards, it's tiny. You can go to Costco and get 7 of those for like $500, 7 5 terabyte drives. But because of the expected and resultant large additional data volume, they went with a distributed system. So you have core sites like DKRZ in Germany, IPSL in France, in the UK, I believe there's one in Australia, maybe Japan too. So you have the core sites there, and then they have all these nodes set up on all the other modeling centers that serve data back to these core gateway sites, as they're called. They all communicate to each other and everything. At the beginning, it was really, really bumpy because the software hadn't been worked out, plus there was a lot of other issues involved. But the same sort of approach will be used for CMIP 6. And I think this time it'll work a whole lot better because we have a lot more experience and a lot more people are involved.
How about CMIP 4?
There was no CMIP 4.
Why?
Well, actually, there was. It was an addendum to CMIP 3. But they jumped to 5 so that the 5th assessment report from IPCC would match the the CMIP number. Because it was AR4 with CMIP 3 and AR3 with CMIP 2. It's a complicated story. So this is what we did for CMIP 5, some details, or CMIP 3 also. A couple models in CMIP 3, 5 different configurations of CSM for CMIP 5. A lot more data required, a lot more fields requested. And I've been working with Sherry Michelson, on helping her set up this tool that I'll explain here in a minute. And apparently the number of requested fields this time around is in the order of 1,800 to 2,000, something like that. I don't remember the exact number. And there's a lot more people involved with CMIP 6 this time than there was with CMIP 5. I'd say probably 25 at this point. Yeah, just people at in-car. So this is what we did with CMIP 3 and CMIP 5. This is kind of a pictorial version. This is what I presented at a CISL user forum back in 2005. This is the way we did things then, and up until now, this is the way we've been doing things. You know, supercomputer, right to the big disk, straight to archive, pull it off archive to some other machine, do your post-processing, nodes, diagnostics, put it on the web portal. I said this was a model that was not tenable, and I was right. So here's an introduction to CMIP 6. So instead of a handful of major projects, there's a whole slew of them, spanning just about every aspect of climate modeling, and taking a look at future scenarios, regional climate, carbon cycle, paleoclimate, geoengineering is going to be a big one, chemistry and aerosols. And this center thing here is called the DEC. It's called Development, Evaluation, and Characterization of Klima, which is the German word for climate. And these core experiments will be starting here very shortly. The rest will be developing over the next few months. So this was the plan. So you always do these CMIP DEC experiments, CMIP 6 DEC experiments, regardless of the model version you're using. So we won't be using CSM1, the older version of the model. All these will be done with CSM2. I don't know if we'll do any more with there'll probably be CSM 2.1, 2.2, 2.3 over the next few years. We'll see how that turns out. And then these different MIPs participate in CMIP 6. So there's like a scenario MIP, land use MIP, ocean MIP, or sea ice MIP, cloud radiative forcing MIP. They've all prepared a list of experiments they want run and what experiments they want run and how much model output they want. All this is being gathered together and passed around and chewed on and digested, and then it's being absorbed by the modeling groups, and they get to pick what MIPS they participate in and how much data they're going to submit. So all this has been worked on for the last, 3 or 4 years up till now. And then we'll see if there's actually an IPCC AR6 sometime in the next few years. So this is our plan for using Silk and all the other tools for CMIP 6, using our experience with the decadal prediction runs as a test. So you run the model, writes to disk, you do the pi reshaper, you pass that to this new tool called PyConform, which is a model translator and converter from the model output to the requirements of the MIP. I did this with this tool called CMOR, Climate Model Output Rewriter, for CMIP 5, which was very slow, serial code. It took forever to do anything, so that was a bottleneck. And so that has been replaced with this tool called PyConform, which has been developed by Kevin Paul and CISL, with a lot of advice from me and others. That's almost complete. Then all that information gets written to HPSS. The output from PyConform will be published into the Earth System Grid Federation. And sometime in the next few weeks at the outside, we'll be doing an end-to-end run of all this stuff managed by Silk and see how it goes. That should be very interesting. As kind of a test case, I took a set of 3 old CMIP 5 experiments that we had done at NERSC. It took 3 days to pull them off tape, about 6 hours to do the transposition using PyReshaper, and another 2 days to run them through my old CMOR codes. So what's that, roughly a week's worth of work, of which actually 6 hours was actually doing the really hard part. The slow part was the CMOR and, of course, pulling stuff off tape. And so this is the timeline from NCAR's point of view. We're somewhere, are we in one of the orange boxes yet, Susan?
We are trying to go back and forth.
So they, what CSM is doing now is they're running WACM, which is the high top atmosphere model with chemistry. Or they have chemistry and all that turned on, right? Then they feed that back into CAM, and then produce new SSTs that feed back into WACM, and then they'll run that with CAM again, and then do these. And the blue boxes here are these long ocean and land spin-ups. Ocean takes a long time to run to get it into at least a semi-equilibrated state. Same with land, not quite as long, but you have to get all the carbon cycles or the carbon cycle and various other things into a relatively stable state. And then once those two spin-ups are done, we'll be running a 500-year control with CAM and a 200-year control with WACM. And then at various points along those two control runs, control being defined as an 1850 fixed condition so that the climate is stable, we'll be starting various 20th century runs and other runs. And then I expect within the next couple of months, we'll be filling up Yellowstone like crazy. And all this will be done on, at least this part is all being done on Yellowstone, which is why everybody is being asked to move to Cheyenne. So here's the, from a different perspective, Yellowstone goes away at the end of 2018. Cheyenne is in business now. So for the first part of 2017, I was a little generous here. We actually haven't started any real CMIP simulation, CMIP6 simulations, although there's a couple candidate simulations for a control run, but that hasn't quite been decided yet. Plus, the development of CSM2 is nearly complete. The release of that will be sometime shortly before our workshop in June. There's been a tremendous amount of focus, a tremendous amount of work, a lot of runs, a lot of people putting in tremendous amount of time on getting CSM2 ready. The CMIP6 simulations will be ramping up, so by later this year we'll be going full tilt. Eventually some of them, particularly the higher resolution, the quarter degrees, will likely be run on Cheyenne depending on how much time we have. The post-processing and publishing to ESGF, the orange and green boxes, will begin as soon as the runs start flowing in. And then of course all the analyses and papers fully exploiting the NCAR CMIP analysis platform will begin by the beginning of next year or late this year as runs come in. And I would suspect what we'll probably end up doing is pulling in data from other modeling centers to our analysis platform so our scientists and university scientists can use it to do their own analyses. So this is what I said in 2005 would be the right way to do it. And lo and behold, I think that's pretty darn close to what we're actually doing with CMIP6. So we run the model, save it on disk, do a bunch of data processing on it, archive only that stuff, not the model output. And all of this is interconnected with the database. We actually have a simulation database that Alice Bertini has developed that is going to be keeping track of where everything is in this big workflow. Then everything gets automatically published to the portal. We get our diagnostics, and then we have other documentation on these web pages. So it's taken about 12 years, but I think things are shaping up as the way they should be. So this is a repeat of the previous plot. So the anticipation is somewhere around 2 petabytes of model output will be submitted to CMIP6. We'll probably generate on an order of 5 petabytes. That number kind of oscillates around. I've seen numbers as high as 10. I don't know if that's actually doable in the amount of time we have to do it. We would prefer to do as many CMIP6 runs on Yellowstone as possible rather than shifting over to Cheyenne because that makes analysis that much more difficult. We're near a different machine. So we'll see what happens. And then just as an aside, here's some of the kinds of questions I get from our users. Some of these are amusing. I downloaded 2 files and I couldn't open them on my PC. I tried Adobe, but it did not work. Well, I mean, there's various levels of users out there. This is a person who's probably a really good scientist but isn't familiar with NetCDF. These kinds of questions I try to answer as best I can. I'm usually pretty good at it. But then I'll pass them along to our scientists or ask them to go to our bulletin board. The second one here, that's a surprisingly common type of question. This is usually from people in the GIS world. They want to know what our geodetic model is. We don't have one. The Earth is just a sphere of fixed radius. I mean, I've had a few people, primarily hydrologists, say, you know, when I zoom in my region of interest, and some of the features that your model says are there are like kilometers and kilometers off. And I'm like, well, yeah, it's because we don't have an oblate spheroid. We just have a big sphere. So it's interesting, though. I mean, it gives you an opportunity to talk with people. And I've been to a few conferences where somebody say, oh, you're Gary Strand. I'm like, what'd I do? Because they send me an email, you know, I don't recognize their name or something. So in the near future, as CSM is a community model, we have to do what our community wants. That makes it somewhat difficult. I mean, the entire CMIP analysis platform is a response to the needs of our user community, in that these large data projects generate so much data that even a university doesn't have enough space to store what their scientists would like. So as a community model and a national center, we've built this big analysis platform so university users and others can come in and do their analyses, you know, kind of like using our HPC resource, but this time with data. I still see a future for long-time archival storage, because even though in the past it used to be thought that, well, as a new generation of climate models comes along, you're not that much interested in keeping the old stuff because the new ones are better. Well, climate models evolve and people want to compare against what was done in the past. And it would be great if we had at least the control simulation output for all of our all of our iterations of climate models over time. We can go back about 20 years maybe, but climate modeling here at NCAR goes back before that. It'd be great to have all that data still around for intercomparison purposes. One other possibility, well, we're getting pretty close to this, doing the model and analysis somewhat concurrently, except we do it all on disk. Stuff still gets written to disk. I think in some ways in the future, you'll be wanting to do the analysis in memory with the model as it's running, rather than just saving it to disk, because that's memory to memory is a lot faster than memory to disk and back again. One thing we have to do soon is update our formal data management policy to reflect the new workflow and the way we do things, and the various other changes that have come to pass since it was written in 2011. This sometimes gets some oohs and ahs. The whole ESG and ESGF model, where these modeling centers archive, you know, petabytes and petabytes of data and then ship it around the planet to various people, is that really sustainable or not? To me, that's somewhat of an open question. As I mentioned earlier, the CMIP 5 or the CMIP analysis platform is a response to this not being sustainable. I've seen some discussion of why can't we just pull all our stuff in the cloud or use BitTorrent or, you know, something like that. I don't know if that's really viable, in the sense that we don't typically interact with those sorts of service providers. I know some modeling groups have kind of played around with it a little bit, and other people have looked at it. I am as yet undecided. I'm somewhat agnostic on that. One thing we definitely have to have is server-side analysis, because if you think about it, it's possible to start with 100 terabytes of data, and what you end up with is a 500 kilobyte PostScript file that you put in your journal article. How many orders of magnitude reduction is that? The more that you can do closer to the machine that generated the data, preferably at the same site, using the same hardware, the better. You don't have to bring it all to your local center. And one other thing that may come to pass is HPC has now become so cheap, relatively speaking, it may be cheaper to simply rerun the model to get additional data if some feature or discovery warrants redoing it, in which case all you'd have to save is the exact model state, and plus, you know, these checkpoint restart files, so you can start from some time in the model run, change the model so it dumps out a lot more data or other data, and then just run it again. The problem with this is old compilers aren't maintained. It's unclear if you get the same answer twice. There's already been a lot of work put into checking model output for changes in like compilers or machine ports to see if it's really the same or not. I think bit for bit has had its day. That's just not realistic. And my understanding is with these, exascale architectures, bit for bit is off the table entirely. You will never get the same answer twice. And one problem with that, though, is let's say you have some interesting climate features show up in a run and you decide, oh, we need to save higher frequency data to do a more stringent analysis or look at some additional output. What if it doesn't happen again? Was that just a quirk of the compiler options that you chose, the optimization, or was it actually a real feature of the climate system? We'll see how that goes. And then, of course, my favorite plot, this is NCAR's terabytes and teraflops going back to 2000. The black boxes, at the bottom are our various hardware resources. So you can see there the big jump a couple years ago with the arrival of Yellowstone, a little bit smaller jump with the arrival of Cheyenne, although this is a log scale, and then a little dip at the end of 2018 when Yellowstone goes away, and you can see the future, sometime, let's see, what is that, about 2026, June 17th, 4 in the afternoon, something like that. We'll have an exascale machine. Chances are, though, we'll get to exabytes long before then. Although the interesting thing is the bytes per flop is actually dropping. I think I'm not quite sure why that is. Maybe yeah, yeah. The machines are outpacing the ability of every other thing that they use to keep up with what the CPUs can do. And lastly, some credits to all the people that have participated in all this work. And that's the end of my talk. Thank you.